This is the video lesson for circular orbits. The learning target for this lesson is, I am learning to describe circular orbits using Kepler's third law. The success criteria for this lesson are, I can understand that for a satellite in a circular orbit around a central body, the satellite's centripetal acceleration is caused only by gravitational attraction. So the only thing keeping an object in circular motion around a large central body, so like the moon around the Earth, or the Earth around the Sun, is the force of gravity. And I can understand that the period and radius of the circular orbit are related to the mass of the central body. Alright, in this video we're going to look at circular orbits and how they're different from regular elliptical orbits. So here you can see we've got a diagram of a circular orbit. We've got this central body in the middle, which is M1. And then we've got the other smaller object orbiting around it, which is M2, and it's in an elliptical orbit. So each object is exerting a gravitational force on the other, and M2 is traveling with a velocity v around the object. You can see as the satellite is moving around the main body that the radius is not changing, nor is the velocity, nor is the force of gravity. So in circular orbits, the radius is constant, the gravitational potential energy, U sub g, is constant, and because of energy conservation, since U sub g is constant, kinetic energy is constant, which means that velocity is constant for circular orbits. So let's look at velocity in circular orbits. So when we're looking at forces in circular orbits, the sum of forces are the centripetal force. So we have mass times centripetal acceleration. So we have Fg is equal to m2 ac. So G m1 m2 over r squared is equal to m2, and AC is equal to v squared over r. So our mass 2 cancels, and one of the r squares canceled. So if we're solving for the velocity of circular motion here, circular orbits, we end up with the square root of g times m1 over r. Okay, so some things to note here. Note that m2 has no effect on the orbital behavior. So it doesn't matter how much mass the satellite has, it doesn't have any effect on its orbit. So only the mass of the central body and the radius of the central body, or the radius that the object is orbiting at, affect the velocity of its orbit. So as m1 increases, the velocity of the circular orbit increases. As m1 decreases, the velocity decreases. That should be a decrease. And then we can see here that the velocity of the circular orbital velocity, is proportional to the square root of 1 of the mass, and the velocity of the circular orbit is proportional to 1 over the square root of the radius. Okay, so let's look at energy in circular orbits. So total energy in a circular orbit is equal to minus, so notice that minus sign, g times m1 times m2 over 2r. So let's go ahead and prove this. So remember that total energy is equal to the kinetic energy plus gravitational potential energy. So we have E circular is equal to 1/2 m2 v2 squared minus g m1 m2 over r. And in the last slide, we found that v is equal to the square root of g m1 over r. So placing that back in this equation, we have E is equal to 1/2 m2 times the square root of g m1 over r squared minus g m1 m2 over r. So expanding this, we have E is equal to 1/2 m2 times g m1 over r minus g m1 m2 over r. So this gives us g m1 m2 over 2r minus g m1 m2 over r. So to get a common denominator, we have to multiply this term by 2 over 2. So together we end up with minus g m1 m2 over 2r. Okay, so let's look at Kepler's third law in circular orbits. So from a couple slides ago, we have v squared is equal to g m1 over r. We also know, according to circular motion, that v is equal to 2 pi r over t. So putting these two together, we have v squared is equal to 4 pi squared r squared over t squared, which is equal to g m1 over r. So solving for t, we have g m1 t squared is equal to 4 pi squared r cubed. So then we have t squared is equal to 4 pi squared r cubed over g m sub 1. So notice here some behaviors. As m1 increases, t decreases. So as the bottom of this fraction goes a bit larger, t gets smaller. And also, as the radius gets larger, so as this term gets larger, the period t also gets larger. So in other words, as the mass of the central object, as the central body, so the mass of the planet gets bigger, the time it takes for the satellite to rotate around it, to orbit around it, gets smaller. And as the radius, the distance from the central body gets larger, the time it takes for the object, for the satellite to go around it, takes longer. So mass gets bigger, the time it takes to go around it gets shorter, and as the radius gets bigger, the time it takes for the satellite to go around it gets longer. So what have we learned in this lesson? We learned that gravity causes circular motion. So in the case of orbits, the only force keeping the object undergoing circular motion is gravity. And we learned about the radius and period of circular motion, or circular orbits. So the radius and period of the orbiting object is determined only by the mass of the central body. So as the mass of the central body changes, that's going to change the radius and period of the object orbiting the central body. All right, thanks everyone.